Hello everyone, welcome back. So now I got a group problem and you're watching a video. Maybe you're watching a video with a friend though. Hey, if you really like my videos that much and you're like getting all of your friends together, maybe your entire neighborhood and you're all watching the video together, kudos to you. Kudos to you, and all of you work together as a group. You, your grandma, your friend across the street, whoever, worked as a group to solve this problem. Now let's look and see what we have. Well, we have a simply supported wood beam of 9 foot long. It's got a concentrated load P at mid-span. And you can see the cross-sectional dimensions of the beam are going to be 5 inches wide and 9 inches tall. Okay, that's not too bad. It's kind of similar to things we've seen in the past, so what's we going to have here? Well, if the allowable shear strength of the wood is 100 psi, determine the maximum load that can be applied at mid-span. And we get to neglect the weight because magic. Maybe it's in space. Elon Musk is building his spacecrafts with wood now. That makes sense. Okay, so you and all your hundreds of friends who are there with you today watching this video, go and try out this problem and then come back and we'll look over it together. So, 3, 2, 1, and we're back. Let's try it out. So first off, we got to find out the section properties, which aren't hard. The centroid's right at the center, and moment of inertia is simply going to be the base times the height cubed over 12. So that comes out to be 303.75 inches to the fourth. Now what's the max Q? Well, if it's 9 inches tall, 5 inches wide, then our central axis is right in the middle, and it'll be either the area times the distance to the centroid for the top or the bottom. Either one works. I would probably choose just the top because that's what I typically do. So 4.5 times 5 times the distance to that point, which would be 2.25. And I'm right. So that's the distance to the centroid, and this is the area of that new little section. So we get 50.625 inches to the third. What's our maximum shear force V? Well, we don't know what that is because we don't actually know what P is, but we're going to get it in terms of the applied load. So, with that, actually we're going to do it a little bit differently. We are going to say, okay, our max shear stress is going to be 100 psi. We can't go above that. And so with that, we're going to solve. We're going to solve for the internal shear force that we can actually hold to avoid going above that max shear stress. So we know everything else from this. We know what our thickness is. We know what our moment of inertia is. We have everything else. We know what Q is, and we know what that shear stress is. With all those, we can say that our internal shear force can't go above 3,000 pounds. Now, if we're looking at that, well, what's the max internal shear force we're going to see at any particular point? Well, if we do it in terms of P, we see that, okay, if P's at the center and there's nothing else, then my reaction force is going to be P over 2 on either side. And then with that, you'll see that my maximum shear force never goes above P over 2. It's always equal to, but less than P over 2. So, if my max shear force is 3,000 pounds, then the max load it can carry will be 6,000 pounds. It'll be twice that. So, that's it for this problem. It wasn't too terrible, but thank you for listening. I hope this helps you, and I'll see you all next time. Bye-bye.